A professora Ana Almeida já vai... Ok. Nesta também. Ana, bom dia. Ok. Bom dia, teste. E teste, bom dia. Ouviste também aqui, não é? Correto.
E vamos a isso, vamos dar início à conferência. Para dar início, chamo o professor Jorge, que nos vai aqui dar umas palavrinhas. Obrigado a todos.
Bom dia a todos. Bom dia, professora Manuela Veloso. Bom dia à professora Maria Lourdes Rodrigues, nossa reitora. Caros colegas, docentes, investigadores e alunos, em particular os alunos de Ciência e Dados, e em mais particular os alunos que organizam a FISTA, que é sempre um marco de sucesso do ISCTE e da Escola de Tecnologias e Arquiteturas. Devo deixar aqui só umas breves palavras sobre a professora Manuela Veloso. Eu penso que a maior parte de vós conhece, mas só recapitulando os pontos principais. A professora Manuela Veloso é licenciada em Engenharia Eletrotécnica por um dos nossos concorrentes, mas não vamos levar isso a mal, não é? Pouco depois, fez rumo aos Estados Unidos, onde obteve o doutoramento na área de Ciências Informáticas, da CMU, da Carnegie Mellon University, e imediatamente após ingressou como docente na universidade, sendo atualmente professora catedrática e tendo inclusive desempenhado o papel de diretora do Departamento de Machine Learning de Aprendizagem Automática. Devo dizer que a professora Manuela Veloso é uma investigadora internacionalmente reconhecida da área de robótica e de inteligência artificial. Tem imensos prémios, que não vou estar aqui a descrevê-los. Gosto sempre de chamar a atenção para os prémios que a professora obteve com os seus alunos, que é sempre motivador, e em particular os campeonatos de RoboCup que a equipa dos alunos, com a supervisão da professora, obtiveram. Podemos mesmo dizer que, se calhar, podemos referir a professora Manuela Veloso como a mãe do Cristiano Ronaldo dos robôs futebolistas, digamos nós. Atualmente, a professora desempenha funções num banco de investimento americano, JP Morgan, onde, digamos, está a levar alguma inteligência artificial à banca, se calhar algo mais. E devo dizer que isto também é um ponto que chama a atenção para professores, investigadores e mesmo alunos, que ao fim de 30 anos de investigação numa área, algumas vezes o que nós investigamos durante 30 anos não é exatamente ou não vai ter exatamente a finalidade daquilo que pensamos que tínhamos. Eu acho que, se calhar, nenhum de vocês, alunos, investigadores, pensa que daqui a 30 anos o que estão a fazer vai servir para a alta finança. Mas essas coisas acontecem, de maneira que, mesmo que estejam a investigar, a estudar um tema que vos parece de baixa aplicabilidade, nunca se sabe. Algumas vezes essas coisas que nós pensamos que não servem para nada, para além de nos divertir, de nos motivar cientificamente, de facto, na realidade, têm outras aplicações que nunca pensávamos e que abrem novos mundos. De maneira que a professora é aqui uma inspiração para todos nós e, com isso, passo a palavra à professora Manuela Veloso. Obrigado.
Ok. Bom, bom dia a todos. É um prazer vê-los todos. Eu vou fazer assim, portanto, vou falar, depois, eventualmente, no fim, teremos perguntas, portanto, se existirem coisas que eu falo que realmente que querem aprofundar mais, visto que eu vou tocar em várias coisas, mas talvez o nível de aprofundamento depois venha nos papers, eu também poderei aqui a citação, mas de qualquer maneira, portanto, ou interrompam ou guardem as perguntas para o fim. Está bem comigo? Eu normalmente falo em inglês, os slides, claro que são em inglês, mas no fundo, se há alguma... Quer dizer, há alguém aqui que precisa que eu fale em inglês ou não? Ok. Está aqui alguém? Não percebe português? You guys don't understand English? Portuguese? Okay, that's fine. I'll talk in English. That's fine. Bom, portanto, I'll mix up English and Portuguese, whatever. Okay, English. Okay, English it is. Okay, perfect. Okay, I'll tell you about AI, and I'll focus on the financial services. I'll mention something about robotics later, but let's go. So I'll take the opportunity to insist with you again on the fact that you may also already know that AI, which stands for artificial intelligence. The other day I got across someone who actually did not know what AI stands for, so I hope you all know it's artificial intelligence, is a science, a very young science from the mid of last century, beginning of 30s with Alan Turing, and then the 50s with Herb Simon, Alan Newell, John McCarthy, Marvin Minsky, and so forth. But it's a young science, but it's a science that aims at having all the features of intelligence reproduced in a computer, in a machine. Therefore, the term artificial and intelligence. But you have to understand something, even like when these science started, the point was that these AI, these artificial intelligence, is in fact a science of many components. So, because humans can speak, humans can read, humans can see, humans can think, so it's somehow, this intelligence is a combination of many features. And the field of AI went the same way. So basically, it worries about all processing of all the data, the input to our brain, to our reasoning system, language, speech, vision, but then it focuses also on all the techniques that humans eventually have for planning, searching, machine learning, all the cognitive aspect of humans, and eventually then the execution. We walk, we speak, we take feedback, we execute actions. So think about AI as in fact this integration of all these capabilities. But when you get across some AI research, it might be in only one specific area, which in principle is fine, because it's one capability of these multiple facets of intelligence. So this is the first thing you have to understand, is the science of components. All these different components that eventually are integrated in fully autonomous agents, and that's what I did all my life with the robots. But it doesn't mean that, in fact, there are not components, okay? So let's open our hearts, and if someone works only on deep learning, even if it's just one component, it's okay. If someone works only on machine vision, it's okay. Everything is about these components of AI, okay? First thing. I'll have a homework and a test at the end, so be ready. Not really. But anyway, so then I've worked on this for a long time, and then in 2018, I went to JP Morgan, like George so kindly mentioned, and at JP Morgan, there is this thing about finances. So, and I built a team. We are now almost 80 people, all PhDs and masters in computer science and electrical engineering and math and all sorts of machine learning and AI. It's an AI research group. And therefore, we have these aspirational goals, and I'll share with you the 7 goals that drive the AI research, and then I'll delve into some examples. So, we want to study how AI can predict and affect large economic systems. And I'll tell you about this, and how to liberate data safely, and I'll also mention this, how to eradicate financial crime. Financial crime, fraud, money laundering are all very complicated problems to solve. And in this talk, I will not mention as much financial crime. But then we have these other 3 goals which are related to the stakeholders of the financial industry. Basically, our own employees, our clients, and our regulators. And somehow the 3 of them, you have to use AI to empower the employees, to perfect the client experience, and eventually to agentize this policy compliance. And then there is one goal overarching, which is the concept of having these AI systems be built such that they establish ethical and socially good AI. So the values of society, the trust, the explainability, the ESG, all sorts of values that society has that somehow need to be embedded in all these financial systems. So this kind of like understanding of what is AI research is important for you to see in a financial industry how we are pursuing this goal of bringing AI research and to this financial industry. However, also within the actual science and engineering, here are the research foundational areas, the areas of study that my team is built of and that supports those goals, basically learning from experience, data and knowledge. So if you're interested in JP Morgan, let me know. If you're all data scientists, we open our arms to data scientists, security and secure and private AI, security, cryptography, all sorts of like security kind of like algorithms, machine vision and language, multi-agent systems, safe human-AI interaction, and resources and planning. So that's it. So this was the beginning of my talk, which outlined, this is the outline of the talk. So basically, I told you a little bit about this perception, cognition, and action, or data, reasoning, and action, and execution, the three building blocks of these intelligence. Then I told you a little bit about JP Morgan Chase, and these aspirational goals, and now I'm going to just focus on a few of the projects, and then we'll have questions at the end. Okay? Are we all set? So this was just an introduction, and then we'll delve into this. So let me tell you this, and I told you this before, so I actually don't know if some of you came to my talk a few years ago, and so I'm going to update on this project, but I'll tell you what this is all about. So this is about someone who comes from robotics, entering JP Morgan, and when I was brought to this trading floor, you know, the trading floor, we usually see it on movies. I had never seen it live, but it's like these, all these people standing, and they are all surrounded, really surrounded by screens, by all these monitors full of like time series data plotted on their screens. So this is an example. So you go through these, they kind of, everybody tracks what's happening, and then they make decisions, buy, no buy, buy these, sell these, buy. And it's like this gigantic kind of decision-making, all driven by what at the time, a robotics person entering the field, I understood as images. Before I entered, I mean, so all the trading algorithms, all the algorithms use a lot of math to process these signals and make predictions on the signals, but I could only see images. So I was looking at these screens and thinking, they actually look at this as an image, and they were not using any computation and Monte Carlo simulations and wavelets and Fourier transforms and you name it. Their signal processing was, in fact, a transformation from the signal to an image, which led to the decisions. So I left this room. I was there like about 2 hours. I mean, it was a wonderful visit to the trading floor. They explained all these issues about trading, but I could only see these images. So when I went back to the lab with Tucker Balch, who was there, and Naftali Cohen, Zen, and Srijan joined later, we basically tried to understand if we could break these financial data that was plotted on a screen into actually images, and then train a neural net, so we broke this signal into little kind of like images, and we trained the neural net with the images corresponding to buy, and the images corresponding to no buy. And magically, to tell you frankly, this was a big surprise to me too, the neural net, which is what we trained the machine learning algorithm, that was the one we used, was able to capture that kind of different signal. So, you know, coming from robotics, we use a lot of neural nets to train, to do object recognition, like, I don't know, apples and orange, cats and dogs, tables and chairs, I don't know, bikes and cars. So we have been in AI, in the classification business of objects for a long time. So you take images of objects, faces, no faces, you name it, but it has been about objects. While here I was trying to have these images be plots, okay? So if you didn't take any course on machine vision, so when I say an image, it's really a matrix of pixel values, like white is 255 and dark is 0, and within the 0 to 255, that's a big matrix. And as you had the plot of the signal there, that's where the signal was dark and the rest was all white. Do you understand? So this is like amazing to try to capture as an image the images that humans use for their decision making. Even you and I walk out of the street, look at the sky, it's like kind of like clouds or dark or sunny, and you make so many decisions based on what we see. Do you understand? The reason why I'm telling you this, and I insist on this, you are finishing this data science kind of like a major, and you are going to ingress on some research or some work. And a lot is done in data science about speech and text, a lot. But somehow this concept of images is overlooked. But 2022, Manuela told you here that the future is going to be about using much more images than we have used so far, okay? So if you have a chance of actually thinking about images in the works you do, I think you will be on a path for great success. And I don't have time to tell you all the image work that we have been doing at JP Morgan Chase AI Research, but we have been doing a lot of things, even classifying documents with Nataraj Raman. We have been like using images of documents, actual pictures of the document, to know what the document is about. Okay, as you can imagine, a legal contract is much, much, much busier than eventually kind of a letter you write. And so there are many things that you can see from images. So, and this Mondrian system which we built was able to perform very accurately on the decisions and reproduce the decisions that humans have made up to 95% accuracy. So I've told you these before, but now we didn't stop there. And in fact, I want to show you just one more example of this power of these images. So we did Mondrian C, which was this classification. And now I'm not going to talk about the video prediction, but I'll tell you about Mondrian P, this prediction of the future. So not a classification of a signal, but we actually train the neural net on 80% of the actual signal on 80 time slots, and we gave them the next 20 and trained to have the algorithm predict the next 20. And these images are very compelling, and I'll explain to you what they are. So basically, when you test it, you give like this much, this first part of the signal, 80 time steps, and you ask the neural net to predict the next 20. And the red line, the red kind of like dots, is the prediction of these Mondrian P. And the black part is the ground truth on things that we were checking. But look how compelling it is to see this red area, this red prediction, capture the nuances of the signal just based on an image. So it's actually, so if you have not, this is a technique called in-painting. In-painting is a technique we applied now to signals that enables, for example, in images of a person, if you train on many, many faces, but then if you actually challenge the algorithm, you block part of the image, you mask it, and then the algorithm can fill in what is behind. And I guarantee to you, it puts the eye on the right place, it puts your single nose, and it doesn't put a mouth here, or it does not put your eye here. It's just amazing how it learns to fill in what's missing. And here it learned to fill in what was missing, and the accuracy we have in the paper you can measure is better than any other methods that were used in the past for prediction. That clear? Okay. This is it about images. This is what I told you about images before. I never showed you these Mondrian P results, which are very interesting, and we are now using them for new strategies for trading that take into account the prediction. And we can predict 20 steps in the future, we can predict more, we can predict less. Of course, the further in the future, the less accurate. Okay, done. So now I'm going to tell you about these multi-agent systems. So we are going to switch to another problem. As you see, we are going to switch 3 more times. So let's just now put these images aside. If you have questions, you can ask at the end. And let me tell you about this multi-agent learning. And then data, which is something that I hope to spend more time with. So these multi-agent systems is something very beautiful about the financial world and about anything that you are going to work on. So as you know, George mentioned that I did robot soccer. So the thing is like this, I don't care at all about soccer. I love Cristiano Ronaldo, but other than that, I don't care at all about soccer. But you know what I like about Cristiano Ronaldo? Is to see the highlights with all the goals. That's what I like. I go to YouTube, Cristiano Ronaldo, goals, that's it, one after another. That's really nice. But I don't have the patience to watch a real full game of nothing. You know, nothing happens, just one goal from time to time. It's not really my type of game. But anyway, the point was that this robot soccer was an opportunity to develop algorithms for multiple agents, multiple players to work as a team. Do you understand? So the challenge was, in fact, thinking that there is not a single AI making decisions, but that the success of the task required multiple collaboration between multiple agents. For example, that's not the case in chess, right? In chess, it's one mind against another mind. In Go, it's one mind against another mind. Many things that happened so far in AI have been like a single agent against a single agent, or a single agent making decisions. Robot soccer was an example of multiple agents. Now, in finance, the world of finance is all of multi-agent world. Because as you can imagine, there are all these players in these markets. There are all these kind of interactions between these players. And in particular, there are these 2 categories of agents. There are the market makers, and there are the investors. And the investors know of a few market makers. This is a property of these over-the-counter markets. And if you don't know, just Google what they are. But basically, it's just trading assets. But basically, there is this problem of connectivity. And then there is the action that the market makers do is only pricing a particular asset. So they are supposed to give their investors a price for an action, for an asset. And then the investors, they gather prices from all these different market makers. They have their own experience about the relationship with these market makers. And then they make a decision to transact with this particular one. So that's a very simple game. It's basically you have to be careful with the price you give, otherwise no one wants to transact with you. And the investors may want to sample different market makers. But it's a complicated problem because there are thousands, millions, many assets, and this happens at a rate of many, many transactions per second. Do you understand? So it's a very difficult kind of machinery to really do these transactions. So the question becomes whether we can actually learn these market-making behaviors. Can we learn, by letting them play this game many, many, many times, how to select the right prices, how to actually, with whom do they transact? So we only learned the market-making behaviors, and the investors would have an algorithm to select the one they want to transact with in a fixed distribution specific to the type. But the secret here, and here I want to tell you here, from a technical point of view. So I described to you this problem. So how do you go about writing an algorithm for this? How do you go about writing some kind of a game algorithm for this? So the secret here, let me just show you here, was to represent the market makers as parameterized agents. So you basically assign 2 parameters to every single agent. And you assume that they have 2 variables, one which is the risk aversion, which I'll explain in a second, and the other the connectivity. And now learning becomes adjusting these parameters such that eventually you optimize how much you get over time. So interestingly, we define this as an MDP, so Markov decision process, with observations, actions, and rewards. And I'll just show you this, because I just want to finish by showing you this, that somehow
with thousands of agents, the market makers, also in the hundreds, are able to converge to a behavior. They're able to learn by themselves what's called price skewing. So if you don't know what price skewing is that they adjust their relative pricing on how much they bid and how much they ask, depending on how much they have of a particular kind of asset. And so they are able to decrease the price and increase the price as a function of how much of that asset they have. That's called the position. And what was interesting about this, and I'll show you this, you can go to NeurOps and to the International Conference on AI and Finance, ICAF, and there are papers on this. What's interesting about this is that they're able to learn this strategy, this price skewing, which is quite difficult to get the right balance between this bid and ask and the position. But what you have to understand is that from an AI point of view, they were able to learn this through reinforcement learning. They were able to learn the actual balance. So this is an example of multi-agent systems applied to this world of trading, these OTC kind of markets, and showing that they can learn. So the paper shows you the exact algorithm, but at least you know that it is possible to really learn. One final thought is like this, and this is important for later. One final thought is like this. You can ask me, Manuela, but I mean, how do they learn? I mean, what is this kind of like playing games against each other? So, you know, how do they know which actions to select, which price to give? This is all calibrated by real data. So you have the real data of the prices that market makers assigned, and then you are able to use those real data, to adjust the ranges, to calibrate the exploration that is done during learning, okay? So, and now we'll move into this real data thing. We are going to delve into the data in a second, but before we go on with, let me just give you another example. Another market maker simulation, instead of learning, which they can learn, basically tries to explore different types of agents. So here, instead of having market makers, so we tried many things, market makers, investors, and then you can create other agents like momentum agents that have some kind of like response to the stock market, other agents, zero intelligence, experimental agents. We can do all of these and then try to see what comes out. And the interesting thing here is that you can, and this is fundamental for you to understand, you can, through simulation, create data from these markets that was never the real data, but it's extremely feasible. It's real good market data. And this is the beginning of something that is the only thing you have to remember today, if you can remember one thing, is the beginning of our synthetic data research. And I will delve into this on data. Now we're going to delve into data, but I'm going to just, the other three things don't matter, the other two things don't matter much than data. Okay, so let's go and think about data. You have data science. I am 100% sure that all of you did some project in your course that had to do with real data, real climate data, real data of some sort. So real data is precious because it's real. It's real, really, what did people buy, what people did, it's real. However, real data, imagine in the financial industry, is a little bit difficult to access. It's a lot of data, and it's difficult to access these real data. And sometimes for privacy issues, it's not even possible to access the real data. Do you understand? So in some sense, this real data is so valuable, but has also a flaw that at the same time can be a benefit. It captures reality. Real data is going to tell you how much did this person buy in the supermarket, where did they go with GPS, which restaurants they went through, everything. It's all real.
They cannot say, what if Manuela had gone somewhere else? So you don't have the ability, this is very important for you to understand, because you are going to be overwhelmed in the companies you'll join, even me at JP Morgan, by the value of real data. You know, now people say data is like the wealth of someone. I mean, they sell the data, the satellite people sell the data, everybody sells data. However, you have to understand something. You are going to be in these firms, not just data scientists per se processing the real data, but you have to aim higher. You have to think about how can I bring all that I learned here to enable a company, to enable research to do something new. You have to think about the ability that you'll have to project different strategies, to find different markets, to propose different types of policies. So there is this concept of like innovation, very helpful. And you guys being here, wherever you go, you are equipped with this ability to innovate. Innovation is something that is one of the most beautiful things, have the freedom to innovate. But to innovate, the real data is a problem. Because the real data is only going to force you to repeat what was done in the past. So you're not going to be able to use real data to imagine what-if scenarios. And because of this, we actually have, in fact, from day one, when I was at JP Morgan, 2018, July, the first day or the second day, again, I had one of these meetings with all these data people, I forget what the data was about, but there was all these things about data being very hard to access. Even like, I asked, once I got payment data, it was 90 billion records. 90 billion records. I said, it doesn't even fit on my laptop. Why do I want 90 billion records? They're in the cloud. Okay, wow, oh my God. 90 billion, it was all billions, trillions. And so in that day, I immediately said, okay, well, hold on a second. I need a sample of the whole thing, and I want to get rid of this data, but simulate the processes. So there is this, the reason why I insist on this is because if you go out of this room and say, oh, Manuela is saying that we like synthetic data, or simulate, everybody's going to say, no, real data is what matters. It's not true. Real data is very useful, but you are not going to be able to go out of the current unless you experiment somehow. And to experiment, you need synthetic data, you need simulated data, you need to have the ability of like imagining. And I tell you one example. So you all know about AlphaGo, right? AlphaGo is this algorithm that was able to play, again, this game of Go against a real player, in fact, a champion of the world, and basically won. But how did the AlphaGo worked? Well, there were 100,000 or something like games, real games of humans playing Go that were digitalized. And yes, the machine used those to learn what people had played and how did they win. However, what AlphaGo did more was that it ran against itself, given the rules of the game, over and over and over and over, independently of whether any human, any game of the past had been like that. This is called exploration. So you explore beyond what you can exploit, which is the real data. So real data is very good, definitely, but it needs to be used to learn what people are doing, but not to innovate. To innovate is much harder to do with just real data. Do you understand? Is that clear? So it's not that I don't value real data, but synthetic data is amazing in terms of like freedom of thought, freedom of development. You don't need any permissions to use synthetic data. At JP Morgan, we have a site, and you can see on my website, that gives you access to all this synthetic data on markets, on fraud, on money laundering, on customer journeys, on all sorts of like things that are real financial problems, and they're all synthetic data. You understand? Is that clear?
Of course, one final thought. Look, the synthetic data is constrained by what is feasible. For example, in chess, the synthetic data cannot make like the pawn move like a queen. It doesn't make any sense. So you have to constrain the actual synthetic data to be of legal within that world. So you cannot do outside of the boundaries. Also, the real data gives you a very beautiful concept of distribution. How many times did people move the pawn 2 steps ahead when at the beginning of the game? How many times did people move the queen like this? So it gives you a distribution of strategy, which you can use in the synthetic data or not, or you can diverge. But at least you know the space, and then you can decide how far you move within that space. Do you understand? So it's not to get rid of these real data, but you need some freedom in your algorithms to go beyond the real data. Is that clear? So, very important. So, in JP Morgan AI research, we have done several methods to do this specific synthetic data, and one of them was a simulation I mentioned you, but I'm going to mention now another one, which is this AI planning-based simulation, just for you to understand how can you do this wherever you go, because this is very, very transferable to any place that you are. So, let me just go over this. Let me just go directly to this. So think about payments. Payments is data that basically tell that the money moved from this account to the other account. It can be a deposit, it can be an actual transfer, it can be paying electricity, it can be anything. And all of this is recorded, okay? All of this. And if you can imagine, there are, I don't know, thousands and thousands of these payment transactions per second in the world at JP Morgan. JP Morgan, I think, handles about 20% of all the payments of the whole world, from Italy to China, from Japan to Texas, it doesn't matter. Everywhere, all the payments, when you pay here, a credit card payment anywhere, it probably goes through JP Morgan somewhere. Or if you buy on Amazon, whatever.com, it goes through JP Morgan one way or another. The actual transaction of the money. So think about this problem of how do you create simulated data of payments. Now you want to have payments. So something very important to what we did, so this is an actual, dynamic. It's a dynamic process. There are payments every single minute, every single second. So what we thought about with Daniel Borrajo, which we should get credit to him too, what we talked about was like this. Think about this process. Freeze the world. Freeze. Suppose you want to simulate the traffic on the Ponte 25 de Abril, or you want to simulate how many people go to some restaurant, or you want to simulate anything where people go. You think about this, you freeze the world. When you freeze, you get what's called the state of everything. All the accounts of the world, all the clients of the world, all the agents of the world. Think about freezing everything. If you freeze, there is a state. This is AI at its best, because AI, in addition to the actual data classification, data prediction, is about reasoning. And reasoning requires us to think about what can happen. How do things change? The robot moves from here to there. But if you freeze everything, you get a state. So if you are in some company that you want to study anything, you just think in your head like this: what if I freeze these? How do I represent the state of the world if it were frozen? And then you think like this: how do I go? And here in particular, we froze. We have accounts, balances, employers, and all the millions of facts, but you freeze them. And then you think like this: how do you move from this frozen state to the immediate next state? Through an action. So balances on accounts only change through deposits, transfers, payments, and so forth. So this is a discrete world, so it's like playing chess. This is not like how the weather changes or how the waves move. It's not continuous. All of these are state, an action, new state, an action, new state, an action, new state. Do you understand? So many things, not like the motion of cars, but where we have breakfast, where we have lunch, it's all, there are many things that are of this discrete nature, that are not continuous. The decisions we make, the things we do, are of discrete nature. So you freeze the world, get the description as much as you want, whatever you want as describing this, and in Python, in whatever language you want, you describe. This is why AI is about also knowledge and representation. You have to represent all that state, and then basically you enumerate all possible actions, all of them. And as such, the actions describe how the state changes. And, for example, a deposit is simply an action. If the deposit is some quantity, then the balance of the account is increased by that quantity. That's it. And then if you do a wire transfer, the same thing, goes from here to there. So, interestingly, then we actually, here is an example of applying an action, it doesn't matter. We can, if you generate many, many, many of these actions, millions of these actions, you now are generating the Excel file, the data, all synthetic. Not, you don't save the actions, but you save all these states, and these states are the data. You understand? So this is very important for you to understand. I mean, this is like, what I tell you is like this. This is core artificial intelligence, which is combining state with reasoning, and you get this amazing kind of way of thinking about problems. And if you do this n times, you are generating a sequence of synthetic data of payments that never happened, but they're all legal, because the actions say that the amount of the account went up or down depending on the transfers, on the wire, on the deposits, and so forth, on the payments, blah, blah, and you get all this data. Do you understand? Is that clear? So this is an example of we did, and all these data sets are there. Now, when you are going to see, if you go to our website and you ask for these payments data, there are parameters you have to set. How many accounts do you want to have? What's the probability of making deposits? So you have to select some parameters, and then you press a button, and all these parameters are taken into account, and the data comes out as synthetic data according to the legal actions of payments and according to the parameters that you are interested in having. Okay? If you can start by asking just 10 accounts, it will just do 10 accounts. If you want to start like 100,000 accounts, it will do 100,000 accounts. Okay? Also, similarly, we are able to do fraud and money laundering by doing the same payment simulation with the probability of doing criminal activity in the data. So you can have access also in our website to data that has fraud, and then you can have your algorithms challenge. You can challenge your algorithms to find if you detect fraud, or if you detect money laundering, okay? Which are more complicated behaviors than actual, for example, fraud can be captured by, you are not the owner of this account and you are transacting with that account, and something like this, okay? Okay, so data, synthetic data. Now, I'm going to still spend a little bit of time telling you about another aspect of data that's very important. So, switch, next one. Okay, so this is something that you have to understand like this. When you will be in a company, like me at JP Morgan, we interact with all other sorts of clients and customers and companies that have their own AI and their own computing. And they all represent some data in a different way. So we get like these financial data, which we call financial data, basically, Excel files or SQL or whatever they are files that report numbers changing over time, January, February, or weeks or days, but it's always this concept of change of numbers. It's like when a robot moves around and it sees different images. This is now different numbers that capture balances. It doesn't matter. But the problem is that they are always represented in different ways. This is like unemployment data. This is like macroeconomic data. It doesn't matter. And you have all this data in different formats. Armine Norbarts, who works with me, she actually at some point realized this is a pain. Every time I have this data and I want to use the data for learning, I have to basically write a way to use that data in that format. Until she decided to create an algorithm called Sphinx, which stands for Standard Financial Data Extraction, that is able to automatically standardize the data. Okay? This is also something that you guys are going to face sooner or later, and probably you faced already. Even climate data, or data about where people went for GPS, or email data. If it's Outlook, it looks like something. If it's Gmail, it looks like something else. It's a nightmare from a computer point of view, the different formats in which the data come to you. And the secret, and you probably are too young to appreciate this, but I'm giving you precious secrets. I'm telling you, this is the secret. The secret is to try to create your standardized version of the data, yourself inside of the firm, wherever you are, even for your research, create a standardized version of what you think is this data, a chess game, an account, climate, it doesn't matter. And then you need to be able to transform the data that comes in different formats automatically to your standardized version. You understand? So Sphinx is able to basically only assume the data comes as an Excel file and basically use visual and stylistic cues like visual, horizontal and vertical lines and all sorts of like indentation and font size. And it uses semantic cues, like the fact that it says 3 months ended September 30th is a time period because it says September 30th ended 3 months. Revenue is a financial metric. Here are semantic cues, and uses this stylistic and these semantic cues, and is able to convert into a standardized format. You know, this is one of the things I like best about what we have done at AI Research, is this ability to use these data, transform these into the standardized, and then some other data goes to the same representation. Everything is of the same representation, and in fact, you can use this Sphinx, which is a Python module that is available off of our webpage, and it can produce JSON output and TSV output. But the beautiful thing here is this concept of being able to really standardize data. I don't have time to tell you more, but we have standardized. You know what we have standardized? It's actually HR data, resumes. JP Morgan gets thousands of applicants every year. Everybody submits their resume in some way. I mean, nobody has a standard resume, and which is okay because people have their own creativity, their own ability, want to talk. But for us, it's very hard to go and process all these resumes, except that now through natural language techniques, we are able, and visual techniques, we are able to transform all these resumes, extract soft skills, hard skills, all the reference data, all the factual data, and create a normalized resume. And then as soon as we have the normalized resume, we can do matches to job descriptions, also normalized, and we can process these. Of course, people can always go and find out more, but at least it's the first pass through this, which is what AI is good at. AI is good at, process massive amounts of data, and when it's textual data, very effectively by finding all sorts of connections and connecting the dots between this, giving a chance for everybody to be considered for the jobs. versus like when eventually you have like some resume that is never read by anyone. Okay? So standardization. And now finally, I'm just going to tell you about this DocuBot, which is something that I think I showed you before, which is the ability that we have to basically generate PowerPoint slides automatically. So you can interact with this DocuBot, a bot that does documents. You select like some parameters, which company you want, and this particular set of slides was all automatically generated by DocuBot. So we have this template that says these 10 slides are supposed to be done if we get input from which company, if we get input from like all the parameters I need to know, which period of time, and then you can do this. Also, DocuBot is able to get like corrections, change the color of the figures, center the figures, add blah, blah, do this, do that. You can interact with this DocuBot through language and make these revisions, and magically also, this algorithm is able to apply these specific kind of corrections to the slides. And you can save, and basically you will see that run the analysis, and there you go. Now these are, they have the centered titles of the figures, and they have more stuff, okay? So we are also able to, with DocuBot, to generate all sorts of like reports. So you know, JP Morgan, and I'm sure that any company who will join generates thousands, millions of reports, documents that either for legal purposes or for regulatory purposes or for customer purposes, you have to make available. Those are very tedious to do by hand, and so we have automated that. Finally, one final thing that I want to tell you is that at CMU, I've been working with autonomous robots for a long time, and as you can imagine, when a robot moves by itself here in the building, and here I was following the robot, but if the robot goes by itself, when it comes to your office, you might want to ask, where did you go? So there is this problem of autonomy and the robot having to explain what happened, this explanation problem. And so the robot knows in its own internal language what it did, and internal language is very hard, but we built an algorithm for that we call the verbalization that is able to transform that language into explanations in English of what it has done. I traveled 26 meters. I started from room 3201. So this is all coordinates in its mind, but you have to transform to explanations. So at JP Morgan, we have an explainable AI center of excellence. And basically, we explain pricing decisions, we explain counterfactuals for market strategies, we learn human understanding explanations. This last one, we generate actionable explanations, is very interesting. You know, think about a user that asked for a credit card, and this algorithm decided, no, you cannot have a credit card, or a loan, no. And basically, the user asks, why? What do I have wrong? Why don't I get a credit card? Why don't I get a loan? There are all these things. Now, the algorithm needs to give an explanation why the decision was negative, except that it cannot give the explanation what should you change so that you have better chances next time, like saying, oh, your age, change your age. That's not actionable. I cannot change my age. Change how many children you have. That's not actionable. I cannot change how many children I have. So there is this difference from a human point of view on explanations that are actionable, that you can act on, and explanations that you cannot act on. So if the explanations do not take that into account, they are useless for humans, because how am I going to change if you are telling me things that I cannot change? So this has been like a very beautiful AI kind of explanations in AI problem, and so we have been generating these actionable explanations. So in conclusion, I think I'll skip this, and I'll just say, in conclusion, we have many academic engagements. We have partnerships with universities, and if you are interested as a faculty to apply for a partnership, there is a call, and that will come out. I think that already came out. And we have interactions with conferences, and of course we have also summer interns if you want to come to JP Morgan. And in conclusion, this website, this jpmorgan.com/AI, has most of the publications that I talked about. Feel free to browse them and send email if you are interested on more details. And my website at CMU also has publications, this veloso.html. Okay, so keep in touch, and thank you very much, and I'll take questions. Yes, the non-Portuguese speaker. Everybody can ask questions also in Portuguese if you don't want to speak English.
Thank you, Professor Manuela. Thank you so much for your presentation. It was very knowledgeable for me. Is it possible to go to the special slide?
You have to talk to the microphone. Which slide?
Could you go to
Which
the
slide?
special slide with the prices that you use the autoencoders and use the images to...
Oh, the images. The prediction.
Yes, the most
always
interesting part.
People
I have some general question and some technical question. First, you probably use the autoencoders, and you say that with this way, you could be possible to predict even for 20 time slots in the future. First, which time frame you used, and how you labeled your data, because the data is not labeled.
Next question. Okay.
Next question is about that. You say that JP Morgan provide the synthetic data, not the realistic. So the other platform like Yahoo Finance that the researcher use for...
yes, everybody can use the synthetic data.
Yes, also provide the synthetic data or realistic?
Only synthetic data we can provide.
With the Yahoo Finance also provide the synthetic or not?
Yeah, total synthetic data.
So how we can access the realistic data?
It's on my website. It's here on jpmorgan.com/AI in the website. Okay? If you go there, there's a pointer to the actual synthetic data. Otherwise, send me email.
And about the AI platform.
Okay.
Can I ask?
One more.
About the AI platform, which AI platform you suggest? The AI platform that use the Python or Julia? Because
it's Python. So let me answer your first question. Okay, thank you very much. So the important thing here to understand in terms of like this labeled or not labeled is that there is something that is like you use the real data as ground truth. There is no labeling, because basically you have all these variations of the assets, these functions, and you just use 80% of it and the 20% of the real data to train. So it's the real data that is used. And the others I replied. So any other questions?
Manuela?
Yes.
When you were talking, I started thinking about football. I'm not very keen in football. I'm not also a data scientist, but in my life I run over lots and lots of data. I was thinking about football and about prediction and bets.
Prediction in what? Methods, prediction in what?
And apostas.
Oh, bets, okay.
If you look to an attack, a strike,
Okay.
And you take, for instance, 8 frames of the start of the day.
Oh, very good. Yes.
You can predict if it will be a goal
Very
or
good.
not.
Yes.
And then in some sites I know that they can accept online bets.
Okay.
So you can use that to bet and to get.
Well,
That's an idea. Maybe thousands of people think about that.
okay, but it's actually, I'm not saying it's not a good idea. I mean, but this reminds me of something that maybe you are asking one way or another, which is the uses of technology. So we can actually predict, and I think you are absolutely right that if you watch like someone running in an attack, you can think the end. In fact, this research in painting was done first on images of a basketball game, in which when you see someone with the ball right here in front of the actual basket of the hoop, you kind of know that the next image is going to be the ball going in the air. So we humans are very good at seeing only half of the action and predicting the rest. I mean, it's clear that if you see a ball running in front from a sidewalk and a kid running behind, you know that the kid is going to want to catch the ball. So, there are these things about that we, because of our experience, about what we've seen in the past, can do these predictions. So you're absolutely right that what I showed in this research was indeed this ability to use only half or only part of the images and predict the future. And the reason why we can predict the future is because we were trained in so many examples of that. In fact, the ball went through the hoop and the kid ran after the ball and the strike scored, that we kind of make, one way or another, by magic, we can foresee what's going to happen. Not only by magic, but also by physics. That if there is no one stopping the ball in the air, if you don't see another hand, inevitably there is gravity and the ball is going to go. So both physical aspects of the world and also experience aspects of the world, that the kid runs behind the actual ball. You understand? But that's a very good point. I'm saying that, you can use all these techniques of predicting the future based on images to do whatever, whether it's to bid or not, I don't care, but I'm just saying you can predict. One more question? Yes, hi.
Hi, Professor.
It's not working.
It's okay? Okay.
Yeah.
My question is very simple, I think, is how do you measure the quality of the synthetic data? In that example, for instance, you can't really compare it with real deposits because it might or might not be the case.
A very good question. This is a very good question because there is always like how valuable, how good is this synthetic data? And so there are two things I'll tell you. One, which basically is only good because the format is the same. So in the sense that we have time, accounts balance, so you have no clue. It's like saying that, for example, you go to a supermarket and the synthetic data says that you buy things, so it's true. But there is another level of quality, which is how realistic is this. So if Manuela enters the supermarket and buys one banana, one piece of bread, one whatever, it's not real, because who goes to the supermarket to buy one banana? All these kinds of things. Then it's not real, though it's legal. So the hard part is, in fact, to capture that reality of the distribution. And that you, for example, buy the ice cream with a pie crust, with a fruit, because you are going to have someone over for dinner or something like this. It's this combination of these three things. And that's somehow what we are using the real data. And, as you say, we use these real data to calibrate the synthetic data. But you are right in asking whether this synthetic data, how good is it? So as I insist on telling you one thing. The synthetic data is good for development. Sometimes it's not really
good to get the right patterns of the world. However, the markets data, because it simulated the whole thing instead of just making the actions, it's very good. Because we have, that specific kind of sequence of buys and sells and how the prices changes could have happened. I mean, so it's very good in terms of like the prediction. But you're right that synthetic data is not to be used to get what the data is necessarily about, but it's to play with these parameters and explore, what if this happens, what if this happens, all these aspects. You understand? But it's a good point. And we are in the infancy of using synthetic data in the financial world for actual good decisions or for actually good learning. But it's too, yeah. Yes?
Yeah. Shouldn't you expect your prediction model to start failing from the moment in which you start using it in actual financial markets? Given the size of JP Morgan, it will affect how the market works. So if JP Morgan makes a decision on the basis of this prediction model, the reality will come out different.
It's a good question also, but you have to understand something. They make decisions based on something, right? So they always make decisions. The fact that it's used based on this prediction model, think about this. The prediction model runs every second. So it predicts like this. We act. Then we use that and we predict like things change. So we don't use one prediction model for the whole day. Every single second, the prediction is different. And it captures what the results of the execution. Do you understand? So we are always adjusting the prediction. It's like, for example, in robot soccer, when we do the robot soccer, the ball goes like this. We are always adjusting every time, then hit something all the time. So it's a very, very kind of like real-time prediction, not just once. Do you understand?
If every bank uses the same
No.
kind of approach.
Yeah, we have to be careful here. So this type of predictions is not used yet by JP Morgan in practice. This is a research proof of concept. But many of the things I talked about have not been actually deployed. Because, you have to understand something. JP Morgan works perfectly fine without any AI or with whatever AI they have. They don't need AI for anything, right? They have enough humans that are smart enough to do whatever they are doing well. Do you understand? It's more like trying to understand how much AI can enhance what humans are doing. And that enhancement, sometimes it's deployed, and in fact, I showed you one thing that's actually very beautiful. This one is exactly that I didn't talk about. One of the things that AI has helped most is actually to mine the web. So they wanted to know how many private companies there are. And private companies are hard to track exactly because they're private. However, they have websites. So we did this algorithm to go and grab from the websites all the information about these private companies, their CEOs, the state of investment they are in, all automatically by processing language on all these different websites. That's something that for humans would be very tedious to search, to go through, and the AI is helping tremendously because there are public registration of those companies, which are publicly available, and then cross-product with their websites, cross-product with other information, and AI can put this all together and deliver information that is not available easily just by human searching. So that's something that is actually deployed and being used in the company. The using of images and prediction based on image, that's a little bit harder to convince anyone that is useful. So it's a very good example of something that's still a proof of concept. And there are people that believe it's going to be useful and other people that think that they know better. I mean, that the humans know better, which is fine. You understand? Very nice question.
Thank you, Professor. I guess I had a question that was answered about market slippage when using those type of methods. But my second question is about the image processing in trading and investing. I was intrigued because we see hedge funds and investment banks using more and more quantitative methods, quantitative strategies to beat the market. But I was intrigued that using image processing and reinforcement learning methods in deep learning might outperform the market. Why do you think it is like that?
So the only thing I'm going to tell you is like this. I guarantee to you that no humans are there doing anything but looking at screens with images. Whatever they are doing is based on what that image tells them. So I am a big believer that, there is a lot more that humans extract from images than what we are exploring. If you do an EEG, or EKG, or whatever it is, like if you do like there comes out that little kind of like a piece of paper with this up and down how your heart is moving. The doctor comes into the room and she does not ask for, give me a computer program to analyze how this data is. She looks literally at that type of like visual information and decides everything is normal. Or decides, no, you have a problem here. How is that? Magic. So what I'm telling you is like this. We use information that's available visually much more than all this math is capturing. I'm telling you, it's my opinion and I will stick to it for a while. And in fact, JP Morgan might give us a fund to use, to invest just based on images, and we'll see.
Do you think that the image processing would be helpful to build synthetic data? Or more helpful
in fact, we have been doing this, and I didn't have time to explain, but we have been doing, send me an email, I'll send you some papers on this. We are doing
Thank you very much.
Thank you. Yeah. So images is something that, when I was 20 years ago, or maybe 30 years ago, natural language processing was always kind of like very much from the beginning of AI, language and so forth, but not as much speech. Speech is much more recent, though it's still 30 plus years, but I think that images, we have been doing computer vision for a long time, but of objects. Like I told you, chair, tables, cats and dogs. But not really images of other things, like a chart. So you know what? There is a paper, probably this paper by Herb Simon, which says an image is worth 1,000 words, right? So we all know this saying. And in fact, he shows this example that, pulleys, Holdanes pulleys, it's impossible to explain the equation of the pulleys, the length of the lines and the position one's up, one down, without drawing a picture on the board. You just cannot describe, there is a pulley with like one arm of these 5 centimeters and the other one holding another pulley up there. How do you do this? So in some sense, that paper is about saying that geometry. How do you teach geometry without images? So there are many things that we, from a reasoning point of view, our brain processes as images, and it's not text, and it's not speech, and it's not sensing, but it's actual visual information. So I think in data, we have a lot of Excel files, we have a lot of like SQL data sets, we have a lot of data, but we are somehow undervaluing the value of images. I'm just telling you, get ready and be creative and use images, and not just cats and dogs. Do you understand? Cats and dogs are of no interest. And the reason why cats and dogs are of no interest, or tables and chairs, is like this. Cats, dogs, tables, chairs, they will be cats and dogs for eternity. There will not be going to be a new cat now coming, I don't know, with 3 years that you have to adapt to. Now, decisions, there are these kind of like very dynamic decisions. That's of a challenge to use those images, or your EEG or something, or an earthquake kind of data. All these, anyway, I made my point. Enjoy. Wherever you go, vision, images are important for decision making. Okay. And final question. Okay. Yeah. So let's, please.
Hello, good morning.
Yes.
Thank you for such an insightful insightful talk. I have just a couple of questions. So, circling back to the aspirational goals slide.
Yes.
How, more specifically, the part about ethics and values.
Yes.
How do we tackle the challenges with social and ethical nuances?
Yes.
Because it's not brute data; it's much more nuanced.
Yes.
Also, my other question is about the collaboration and the interaction between market makers and investors.
Yes.
Okay, there is good points to be made in that types of interactions.
Thank you.
But does JP Morgan also explore collaboration between different trading strategies within JP Morgan, because they may affect each other, or is only between different elements in the market, such as investors and market makers?
It's a very good question. So I interpret your second question more about like whether in fact this is about more of a game, adversarial game or collaborative game. It's a little bit a general sum game in the sense that there are collaborations that all become like part of the simulation one way or another. So yes, that's true. For the first question, I was hoping to have more questions along these lines. This is very important, which is the ethical values of AI, the ability to really care about values of society. So this is a very heavy debate, whether AI is going to be like, for example, in terms of work, is it going to be putting us all out of work, out of our jobs? I don't know. Mine, I hope not, but who knows? But also, is it going to be able to be transparent and explainable? Also, is it going to be able to be not biased and make decisions that are not biased? So there are many values that, or even like ESG kind of like decisions, or abiding by the Paris Agreement on climate for your investments, who knows? So this is all complicated. Because when a machine is going to make all these decisions, you have to make an effort when you code the system to take those things into account. And I tell you one final thought here. Somehow the responsibility is on us humans to make a good use of AI, because AI doesn't exist by itself. So if you don't use the right data, if you don't let it like create explanations, you have to write the code to abide by these principles of society. So, and one final thing here is that people usually point about the future of AI. Is it going to be bad? Is it going to be bad? And you need to understand, and Herb Simon at CMU said this several times, that we are not, neither of us is a spectator of the future. We are all actors of the future. So somehow you need to be in your heart someone who wants to do the right thing to the AI in the future. Because who is going to actually decide? It's us. We are the programmers, we are the ones that have the data, we are the ones that think about how to solve problems, which problems to solve. So somehow we are all actors of the future and not just spectators and point, oh, they did this, they did that. Why? I can do as much as they can. Do you understand? So this is very important. And I would love, in fact, one other time I come, I'll ask Professor Maria de Lourdes to actually meet with you personally, because you know what? You guys are not, you have to understand the responsibility you are going to have. You finish this program, and now you will be the leaders of the future. You will be in charge of everything. Can you believe? You'll be I don't know. You'll be in charge. Do you realize what's to be in charge? There's a big difference between being a student and become in charge. So you better be in charge well. Do you understand? Good luck. Very good. Thank you very much. And congratulations for 50 years. Right? Very nice. Okay.
Bom dia a todos. Antes de mais, agradecer esta conversa tão interessante, porque mais uma vez foi uma conversa que, como disse a Manuela muito bem, veio pegar em pistas que deixou aqui há uns tempos, alguns de vocês ainda cá não estavam, mas que o ISCTE soube acolher no seu coração e, mais importante que isso, os alunos que entram no ISCTE sabem acolher no seu coração, que é a esperança de um futuro que não se conforma com aquilo que já existe e estão aqui para, juntos, nos prepararmos para atuar e melhorar o que já existe e sermos, tal como disse a Manuela, responsáveis naquilo que vamos fazer. Nós vamos ser responsáveis naquilo que vai acontecer no nosso futuro, porque somos nós que o fazemos. Queria também agradecer à FISTA 22 a oportunidade de tornar esta conferência, de ocorrer esta conferência aqui e de ser exatamente o evento iniciador de uma festa que é feita pelos alunos, para os alunos, mas na verdade para toda a comunidade ISCTE, e onde é reconhecida a qualidade dos licenciados da ISTA, que já têm pergaminhos reconhecidos externamente. Mas este ano é um ano muito especial e daí esta conferência a abrir a FISTA. Este ano vamos ter os primeiros licenciados da licenciatura em Ciência de Dados em Portugal. E se o ISCTE não tem apenas qualidade e capacidade para ser mais uma vez pioneiro na criação de cursos emblemáticos e capazes de responder aos desafios da sua era, estes alunos são os maiores embaixadores desse espírito, inquietos, inovadores, exploradores e acreditaram, e são muito corajosos, porque acreditaram numa licenciatura que não existia em Portugal e ainda não tinha tradição no resto do mundo, estava a dar os primeiros passos no resto do mundo, que é inerentemente multidisciplinar, que captura as sinergias possíveis aqui do ISCTE e, obviamente, noutros sítios, mas principalmente aqui no ISCTE, captura muito as sinergias, as colaborações e o trabalho conjunto e colaborativo entre várias sensibilidades, várias perspectivas e tenta trazê-las e trazer o melhor de si para estes alunos poderem vivenciar essa experiência e essa colaboração, e eles próprios também nos ajudaram nestes 3 anos que já existem de licenciatura a perceber melhor aquilo que podemos fazer e como podemos atuar neste mundo pelo qual somos responsáveis. E tem sido uma viagem muito interessante, que é agradecer a todos, em especial, obviamente, aos que são finalistas este ano, mas ainda aos que estão no 2º ano e aos que estão no 1º ano, que são também eles ainda muito corajosos, porque, mais uma vez, não há tradição ainda, e estão a apostar em passar 3 anos connosco e que isso vai ser significativo para a sua vida. De facto, este é um espaço para crescer. Obrigada a todos, obrigada à FISTA.